Hello. So this time we're going to work on a problem on related rates, and it's stated in the following way. It says a 5-meter long steel beam is leaning against the wall. The base of the beam is pulled away from the wall at a rate of 0.5 meters per second. Find the acceleration of the top of the beam when the base is 3 meters away from the wall. Well, for this, probably what we need to ask first is what are the quantities involved. The first one that I can find is the distance from the base of the beam to the wall, which is indicated here. Another quantity that might be of interest for us is the distance from the top of the beam, well, to the point of intersection between the wall and the ground. That one indicated there. So what we're going to do is name those quantities. We're going to call this one x, and we're going to call this one y. That way we can extract some additional information and, well, essentially get rid of the picture that we have here and obtain something that is just based on trigonometry, because, well, it's understood that the angle here is a 90-degree angle. So what we have is basically this picture, right? We extract from here. We have a 90-degree angle. We have these points, this one is this point corresponds to the intersection between the ground and the base of the beam, and this one corresponds to the intersection of the wall and the top of the beam. The distance indicated here in the hypotenuse of this triangle is 5, as is just the longitude of the beam itself. This one is what we call y, and this one is what we call x. Well, based on this observation, we have the following. So, x squared plus y squared is equal to 5 squared, in virtue of the Pythagorean theorem. Now, what else do we know, right? And what else is that we have in the problem? Well, based on this language, we also have that the derivative with respect to x of x with respect to t, is equal to 0.5. And moreover, note that there is nothing indicating in the problem that this quantity is changing over time. So this is constant. That means, right, that the second derivative with respect of x with respect to t is equal to 0. Okay, this might be useful later as we compute things. What is it we need to find? Well, we need to find the acceleration of the top of the beam, right? This is indicated here. But that means that in symbols, we need to find the second derivative of y with respect to t, right? That corresponds to acceleration. Okay, but how do we obtain these quantities, right? How do we relate them? Well, we're going to relate them through this equation, right, that we have here. So, what is the first thing that we're going to do is first differentiate with respect to t. What is it we're going to differentiate? Well, this equation. On that regard, we have the following. We have 2x dx dt plus 2y dy dt is equal to 0. Or equivalently, right, we have that x dx dt plus y dy dt is equal to 0. Well, that means that we can now introduce the second order derivatives, right, by taking another derivative with respect to t. So from this equation that we have here, we'll just differentiate one more time with respect to t and obtain the following expression, which would be differentiate both sides with respect to t, x dx dt plus y dy dt is equal to d dt with respect to 0. And from here, well, we obtain this x times the second order derivative of x with respect to t plus the x dt times dx dt plus y times the second order derivative of y with respect to t plus dy dt times dy dt equal to 0. Okay, we may simplify this expression into the following, which now is x plus dx dt squared plus y times the second order of y with respect to t plus dy dt squared equal to 0. So this will be our guiding equations. Now, all that we need to do now is to simply indicate the values associated with the unknowns, right? So we have this. When x is equal to 3, which is what is important to us, right? We have the following. We have first that y is equal to 4. All that we need to do is to solve this equation for y, and keeping knowing that y must be positive or 0. What else do we know? Well, just from here, right, we obtain information about dy dt. So then, based on this equation that I'm underlying here, we have 3 times 0.5 plus 4 times dy dt is equal to 0. Right? So, solving here for dy dt, we obtain that dy dt is nothing else but negative 1.5 divided by 4. Okay. Why is that I'm doing this? Well, because look, all that information is going to be needed in order for us to obtain this piece of information. Right? Okay, so now then we have x is 3. The second order derivative, right, of x with respect to t is 0, right? That's something that we know from the problem itself. Plus, well, the square of the velocity in the x direction, of course. That would be 0.5 squared. That's what we have from here. Plus y, 4, times the second order derivative of y with respect to t, plus, well, this one which we computed, equal to 0. Okay, well, based on this observation, what is it we can do? I think we're done. So we have that 4 times this is equal to negative 0. Well, that one, which is just from this part. And well, this one being a square, it loses its sign. So, but then we just subtract it from the equation to isolate this portion. So now we have minus 1.5 over 4 squared. And from here, well, we can just make a division to finish with this. And now we get negative 0.5 squared minus 1.5 over 4 squared, all of this divided by 4. And with this, we conclude. I hope that you like it. Take care.